Okay, so today we start the third chapter of the course, and it's entitled Differential Equations and Quantum Mechanics. And so we'll take a somewhat different point of view now. As you'll see from time to time, we'll dive back into functional analysis, but there will be somewhat different context, more or less for the same problems. So let me perhaps fix the setup. So now in most of the cases, our Hilbert space will be L2 of Rn, and we'll be looking at the physics-motivated operators. So here, delta is the Laplacian. So here there are some physics constants, the Planck's constant, the mass of a particle. So V of x is a potential, and of course we want this operator to be self-adjoint on some domain. So before we had some kind of criteria which tell us in which cases such operators are self-adjoint. So in many cases, or maybe in most of the cases for now, we'll put all these constants equal to 1. Actually, this 1/2 is somewhat negotiable. From time to time, I will put 1/2 also equal to 1, or maybe I'll keep it on some occasions. So let me now give you some small table. So before we were looking at this functional analysis, or more precisely at the spectral theory. And now we're looking at the same topic from the point of view of differential equations. So let me write the same equations, but in a somewhat different context. So here in the spectral theory, one reasonable question that we can ask for is eigenvalues and eigenfunctions of the Hamiltonian, right? Here, the reasonable context for this question is psi in the domain of definition, whatever it is, of H, and in particular in L2 of Rn. So the corresponding problem here would look something like this. So let me still keep for a second the constants. So right, so if I write it down, so this turns out to be a differential equation, right? There is this Laplacian of psi, and there are other things. So this is a linear second order differential equation. And the reasonable thing is to say that psi of x is in the class C2, right? If V is continuous, then it's reasonable to ask for psi to be in the class C2. So note that there is a difference between these two problems. So this problem is in L2, or maybe in the domain of definition of H. So this problem is in a different class of functions. And this might be relevant for the outcome. So we'll see it in some examples in some minutes from now. So, so the other equation that we're interested in is the evolution equation. So the evolution equation looks as follows. Again, psi should be in the domain of definition of h, or we can actually think of solutions, psi of t equal to exponential minus I over h, ht psi of 0. So this is the evolution operator. And since this guy is a unitary, this equation is now defined over all of L2. So here psi should be in the domain of h, but here psi may be in all of the Hilbert space. Now if we write down this equation, we'll get the following PD. And again, so what's the natural place where this PD lives? Well, it doesn't know about any d of h. A priori, it doesn't know about any L2. So this is the equation which naturally lives in C2 of Rn plus 1. And this 2 is somewhat negotiable. Right here, with respect to time, we even don't need to have two continuous derivatives. But OK, if we take C2, that's certainly a reasonable domain where this equation is defined. So you see, basically, these are the same equations on the functional analysis side and on the differential equations side. However, the natural place where they live seems to be rather different. So we'll see what are the consequences of this fact. So these are the two main equations of quantum mechanics. So this is the so-called time-dependent Schrödinger equation, and that's the time-independent Schrödinger equation. So these are the two questions, basically, that people try to solve when they deal with mathematical, and not only mathematical, also physical problems of quantum mechanics. Well, let's put some color around them. All right. So now let's do the following. Let me fix for most of this discussion n equal to 1, even though we'll deviate from it from time to time. So the dimension will be 1. And we always assume that V is a continuous function. So let me denote by S the set of solutions of the following differential equation. So the second derivative is equal to V of x times psi of x. And I would like to recall, or maybe tell you, the following simple fact. So S is obviously a vector space, since our equation is a linear equation. And the proposition says that the dimension of S is equal to 2. So whatever continuous function you take, so you will always have two linear independent solutions, or a two-dimensional vector space of solutions to this differential equation. Probably most of you know that, or how is it? Would you know how to prove it? I wanted to show you a very short proof, or idea of a proof, but just to get a feeling. So for whom this is like obvious? Okay. How would you prove it?
Subtract so that psi of 0 is 0 and psi prime of 0 is 0. And then it's unique solution is 0.
Okay. So that's a good proof. Let me give a somewhat more detailed proof, but it basically goes in the same direction. So let's do the following. So let me denote by phi of x the derivative of psi, and so then of course phi prime of x is equal to psi double prime of x, and well, this is equal, according to this equation, v of x psi of x. So then I can rewrite those two lines in the following way. Let me say that I have a two-dimensional vector with entries psi of x and phi of x, and I consider its derivative. Well, what does these equations say? So the derivative of psi is phi, and the derivative of phi is v of x psi of x. And I can also write it in the following way. Right, so I introduce a 2 by 2 matrix, 0, v of x. Is it the other way? Yeah. Sorry. Is it better? Okay. Oh, now it's correct. Before it was not correct. So, so we see that the derivative of this vector is a 2 by 2 matrix which contains v, which acts on this other vector. So now I traded a second order linear equation for a system of two first order equations. So let me denote this gadget a of x. But now let me recall, right, there was in one of the problem sets, there was a question about the evolution operator with a time-dependent Hamiltonian in our linear algebra part of the course. So we actually know how to solve this equation, right? So we actually know that then psi of x phi of x is equal to, so there is this horrible expression, right, with those multiple integrals. So here will be matrices at of 1, at of n, dt1, dtn, right? So there will be this series constructed from the integrals of a's. And here, well, I chose the point 0, so it will be psi of 0, phi of 0, right? So now V is continuous, so I can take any compact segment and we're going to be bounded there. So all those integrals, all this series converges very well, right? And it defines for us this psi of x, phi of x as a function of psi of 0, phi of 0. So, so then it's easy to see that this thing is a solution to this equation, right? So that's what we checked in the exercise and the problem set. And then this equation is equivalent to these two equations, which means that psi of x that we get here is a solution. Now, here we can choose any of those vectors, and we obtain solutions to our equation. So in fact, this map, it gives us an explicit isomorphism between the two-dimensional space, right? The two-dimensional space of psi of 0, phi of 0, and the space S. So this is an isomorphism between S and, well, depends, right? If we do it over reals, R2, or if we do it over complex numbers, it's C2, right? It depends whether we choose those psi's and phi's to be real or complex. Let me say R2. If we work over C. Right. So let me recall one more small fact which will be useful for us later about these differential equations. Suppose that psi1 and psi2 are two solutions of our equation. Then the Wronskian of psi1, psi2, well, here I never know what's the correct sign. Let's choose the sign like this: psi1, psi2 prime minus psi1 prime, psi2 prime is a constant. And so in other words, double prime is equal to 0. So that's, of course, you can very easily check by just taking the derivative of this expression and using the equation for psi1 and psi2. And psi1 and psi2 are linearly independent. If and only if the Wronskian is non-zero. So that again you can easily check because, right, it's independent of x. This means you can compute it when x is equal to 0. So when x is equal to 0, right, so psi prime is actually phi. So, so this means that this expression, that expression, oh, thanks, which is using psi1, phi 2 minus phi 1, psi 2, right? So this is equal to psi 1 of 0, phi 2 of 0 minus phi 1 of 0, psi 2 of 0. And this is equal to 0 if and only if the vectors are collinear. The vector psi 1, phi 1 and the vector psi 2, phi 2 are collinear, and which means that they are linearly dependent. Okay, so let's look at the easiest example of this situation. So now we'll look at a series of examples. And the first example goes under the name of a free particle. And so this corresponds to the case then of v of x equal to 0. So in the one-dimensional case, the Hamiltonian of our system is simply the second derivative. I now omit all the coefficients, so minus the second derivative. Now let me recall that on the spectral side, how do we define this gadget? So, right, so the idea was that we should take the Fourier transform. So then the first derivative is what? It is, I forgot, is it ik or minus ik, right? I don't quite remember. But in any event, when you take a square, then the square corresponds to multiplication by minus k squared with the minus sign. So this gives a multiplication operator by k squared. And then we take the inverse Fourier transform. So that's one possible definition if we really want to define this Hamiltonian with its domain. Now, what will be the spectrum of this thing? Now it's a multiplication operator by k squared after Fourier transform. So what's the spectrum?
R.
Sorry?
R.
Not really. No. No. Absolutely not. Yeah, it is R plus. It's 0 plus infinity. And why is that? That's because k squared minus z minus 1 is bounded. If z is outside 0 plus infinity, right? And that's what we need, right? So if we are not in the spectrum, we should be in the resolvent set. And to be in the resolvent set, we should be able to construct the inverse operator to our operator minus z. And for that, we need this thing to be bounded, right? So if we step aside from the positive real axis, so this thing is bounded for all k, because k squared is always a positive or non-negative number. So now let's see what happens on the differential equation side. So I must say I was really looking forward to this class, because now instead of this horrible function analysis, we're doing some first year calculus or even probably pre-calculus. So what happens at the differential equation side? Well, what is our Schrödinger equation now? The equation is minus d2 psi over dx squared is equal to e psi, right? So that's the equation that we're supposed to solve. Or, right, or maybe it's okay like this. So now what about solutions of this equation? Well, we know that for any value of e, right, that the previous proposition tells us, there will be two solutions. It doesn't matter what e is. So now for e positive, what's going to happen? So those two solutions, let's work over C. This will be those imaginary exponents. And here k will be the square root of e, right? Now, for e equals 0, there will be again two solutions, right? Constants and linear functions. And for e smaller than 0, well, there will be again two solutions. And here this exponent alpha is the square root of minus e. I guess we're probably right. We all agree on those elementary facts. Now here is a question. Right? No matter what is e, there are always two solutions. But here there was the story of the spectrum, right? We were saying that the spectrum of this self-adjoint operator is 0 plus infinity. But it looks like the differential equation doesn't care too much, right? What this eigenvalue is, right? Maybe one small remark. So if you look at all those functions, do you see any L2 functions there? Not really, right? So actually, at the moment, naively, this problem looks completely disjoint from that problem. So now we'll try to connect them, and in order to do that, we'll have to dive back a little bit into functional analysis. But maybe already here, experts in quantum mechanics, what do you say? So now what does it all mean? What's the relation between this blackboard and the other blackboard? What's going on? Right, so there we don't have any eigenfunctions which would be, so there is, it looks like a lot of eigenfunctions, but for any e, and here there should be some difference between this 0 infinity, right? So these two cases should be really different from that case. What is that difference? So experts in quantum mechanics, why are you silent? All right, so let's dive a little bit back into functional analysis. And here I must admit, so I forgot to remind you one important fact from functional analysis. Perhaps it would have been more natural to do it 3 classes ago, but we do it now. So, so recall, or maybe for those of you who haven't had a functional analysis course, remind you. So something which is called a closed graph theorem. So it says the following. Suppose that the operator acting from H to H, that is, the domain of definition is H, is closed. Then A is bounded. So recall, we were discussing quite a lot those closed operators. And maybe at first sight it seems to contradict our discussions before, because self-adjoint operators, bounded or unbounded, they are all closed. However, notice that typically our unbounded operators, they have a domain which is smaller than H. Now, it turns out that if the domain is equal to H and the operator is closed, then it has to be bounded. You cannot have an unbounded operator. In fact, there will be a small exercise for next Wednesday to prove the other implication. If A is bounded, then it is necessarily closed. So that's an easy fact. So this fact, so how many of you, probably those of you who had a functional analysis course probably saw it. So this is not an entirely trivial fact. So those of you who are interested, I encourage you to check how it works, but we won't have time to dive into it so much as to prove it. Okay. So now maybe maybe let me prove the following proposition, which will be useful for discussion of our interesting situation with a free particle. So suppose that A from D of A to H is self-adjoint. So then a point Z belongs to the spectrum if and only if there is a sequence of vectors in the domain of definition of A such that the vectors A minus Z times UN converges to 0. Perhaps a remark before we discuss an idea of a proof of this fact. Suppose that Z is an eigenvalue. So suppose there is, sorry, maybe here I should add one more condition. Let me normalize UNs to have some norm, let's say, equal to 1. So there is a sequence of vectors of unit norm such that those images converge to 0. So suppose that Z is an eigenvalue. Suppose that there is a vector in the domain of U such that AU equals ZU. Then, of course, we can normalize U to be equal to 1. So then, of course, this Z is in the spectrum because we can choose UN equal to U for all n, right? So then this expression is simply 0. You don't need to converge anywhere. But this tells us that, in fact, to be in the spectrum, so this condition is a lot weaker, right? You don't need any relation between those UNs, but this convergence, right? So it's a lot more flexible. So one thing is to be an eigenvalue, but actually to be in the spectrum, you can have this. You can have this stuff. Okay. So let me give you an idea of proof. Why is it true? So I always confused in which direction, it's easier. Yeah, so let me try to go first in that direction, right? So we have this sequence, right? So we have un, the norm is equal to 1, and let me denote them by Vn, those guys. And this converges to 0, right? So by absurd, assume Z is not in sigma of A. Right? If Z is not in sigma of A, then this means it's in the resolvent set of A. And if it's in the resolvent set of A, this means that we have an inverse, right? So A minus Z is an invertible operator. But A is self-adjoint, so A is closed. So A minus Z is closed. So this means A minus Z inverse is bounded. So we have a bounded inverse for A minus Z. But I think this is clearly a contradiction, because the norm of A minus Z inverse is bounded from below by the supremum, of what? Of un, which is equal to A minus Z inverse of Vn divided by Vn, right? So the norm is the supremum of all those things for all Vn, but now we just choose this sequence, right? So this is a bound from below on the norm, and the norm of that guy in the numerator is 1. So it's the supremum over n of 1 over the norm of Vn. But the norm of Vn tends to 0, right? According to our assumption, right? Vn is A minus Z un. So this converges to 0. So this guy tends to 0. So this supremum is simply infinite. So this guy is clearly unbounded. And this is a contradiction. Okay. So what about the proof in the other direction? Well, the proof in the other direction, now we assume that Z is in sigma of A. And we would like to construct that sequence. So we would like to see what is this sequence of UNs. So let me first make a claim. So A is self-adjoint, so it has this family of spectral projections, right? This projection-valued measure. So in particular, I want to claim that all projections which correspond to the small intervals around z, they are non-zero for any positive epsilon. So this is my real axis. That's the point z, and I'm taking all those intervals around z. Of course, to each subset, to each measurable subset of the real line, I can associate the spectral projection, and I claim that all those spectral projections are non-zero. So why is it true? That's because of the following. Assume this is not the case, right? There is some epsilon for which it's 0. Is 0. But then, in fact, it will turn out that z is not in the spectrum. It is in the resolvent set. So, so that's because if I define A minus z inverse by this formula, right? So suppose I define my A minus z inverse by this formula. So then you see what happens. This projection valued measure, right? This PA of lambda, it doesn't change here. So when I define my, my integral using the Riemann sums, right? So there will be no contributions from this part. And this means that this function is actually bounded on the support of the measure. But if it is bounded, the whole operator is bounded. But if the whole operator is bounded, then we are not on the spectrum, we are on the resolvent set. So we cannot allow for those spectral projections to vanish. Okay, so if they do not vanish, let's do the following. Let's choose un to be in the image of PA, and here let's say z minus 1 over n, z plus 1 over n. And let's choose them of norm 1. Why not? So then A minus z un is equal to an integral lambda minus z dpa of lambda times un. But now notice, so this guy is in the image of that spectral projection. So actually this integral, which is a priori is over R, I can change the integration domain. Well, so I can change the integration domain and replace it by z minus 1 over n, z plus 1 over n. Right? That's because this guy is in the image of that spectral projection. But then if I want to estimate the norm, I can now estimate it using this function. So this function, the absolute value of this function here is bounded by 1 over n. Right? So it's more equal than 1 over n the norm of un. Now it is clear that this converges to 0 when n goes to infinity. So that's this sequence that we want. All right, so after this dive back to functional analysis, we'll go back to the free particle after the break. All right, so should we continue? So now let's go back to the free particle, and I'll consider the situation when E, the energy, so to say, is bigger than 0. And let me introduce the following piece of notation. Let me define a function from 0, 1 to 0, 1. Which will be C infinity. It will be equal to 1 near 0, and it will be 0 near 1, and it will be monotonously decreasing from 1 to 0. So there will be a plateau here, a plateau there, and then it will be decreasing. And then from this function, I will construct a family of functions, chi n, from R to 0, 1. And well, if you want, I'll let you write the precise definition, but I will do it by drawing. So this will be minus n minus 1, minus n minus 1 and n. So this function will be equal to 1 in this middle part. It will be equal to 0 over there. So here I will take my chi and I will transport it here. And I will flip it and transport it there. Oops. For this descent. Sorry, I'm not sure my flip is perfect. So this is a copy of chi, which is shifted by n minus 1. So that's a flip of chi. All right. So now let me choose one of the functions. Let's say the complex exponential ikx, and so k is equal to the square root of e. I can also take the minus 1 as you like, and so let me introduce those products. So I multiply the function psi n. So this will be product of psi of x times chi n. Well, now let's apply the operator h minus e to psi n. So this is equal to psi n minus psi n double prime minus e psi n. And well, what will happen? Let me write it down. So that's the second derivative of that guy, right? So this will be, what will it be? So it will be k square chi n exponential ikx plus 2 ik chi n prime exponential ikx plus, minus, I guess, minus chi n double prime exponential ikx, and minus e is equal to k square minus k square chi n exponential ikx. So this will be, that's what we are getting, I think. So these two terms will cancel out, and we're getting minus 2ik kn prime exponential ikx plus kn double prime exponential ikx. All right. So now let's make some estimates on L2 norms of these two things. So the L2 norm square of psi n. So this is equal to the integral over r psi n of x squared dx. And note that this phase factor will simply disappear, right? So this is equal to the integral over r chi n squared dx. Just looking at the graph, this is bounded from above by 2n. This is bounded from below by 2n minus 1, right? Now what about the L2 norm of this guy? Psi n squared. So that's the L2 norm of this thing. So this is equal to 2ik n prime x squared dx. Now it's actually kind of nice. Again, the phases will disappear, right? Because it's a common phase. It goes away. And this is the real part, and that's the imaginary part of this expression. So this is equal to 4k squared, the L2 norm of chi prime plus L2 norm of chi n double prime. Now, you see, with this chi n, basically its derivative here is 0, its derivative there is 0. So the only contributions come from these two segments, right? And those contributions, they're independent of n. It doesn't matter what n is, right? So this thing is some constant, this thing is some other constant. They are independent of n, whatever they are. So we get 4k squared times a constant c1 plus some other constant c2. Okay. Now let's do the following. Let's say psi n tilde is equal to psi n divided by its L2 norm, right? So this is a function of L2 norm 1. Obviously, the L2 norm of this new thing is equal to 1. well then, what can we say about the L2 norm of this function? Well, it is equal to, so we'll eventually have to put a square root, right? So, so here there will be some 4k squared c1 plus c2 square root. That's the L2 norm of h minus e psi n. And this is divided by the L2 norm of psi n. Okay. So that we can estimate from above using this estimate, right? So this, there is an estimate from below on the L2 norm of psi n. So this is small or equal to this funny constant, whatever it is. This is independent of n, and here this is the square root of 2 n minus 1. And of course, this goes to 0 when n goes to infinity. So we actually constructed out of this exponential ikx, we constructed a family of functions. Now all these functions are well in L2. They are very nice and smooth. They are in the domain of definition of everything. And so those functions, they all have norm 1, and h minus e on those functions, it tends to 0. So these are some kind of approximate eigenfunctions. So exponential of ikx is not a true eigenfunction because it's not normalizable. However, those guys, they are approximate eigenfunctions, and now we can conclude that E is in the spectrum of H. In fact, one of the exercises, actually I think that's a homework for next Monday. It lets you discover what happens for E equal to 0 and for E less than 0. In particular, an important question is as follows, right? For E less than 0, this shouldn't work, right? We don't want E less than 0 to be in the spectrum because it is not in the spectrum, right? It would be really bad if it worked the same way. So, so we let you discover what, right, this argument has to break. For 0, it should be still okay. 0, it should be still in the spectrum. But if you go below 0, it shouldn't work. And next Monday, you will tell us why it doesn't work. So that's the argument which tells you why it works for E positive, but for E negative, it cannot possibly work. All right. Now I would like to pass to the second example, and the second example that probably going to be boring for people who learned quantum mechanics and physics, maybe less boring for mathematicians. Even though towards the end, we'll see whether we have time, but hopefully there is something interesting for everybody. So the next example is called the harmonic oscillator. That's one of the big hits of quantum mechanics. Harmonic oscillator. So here let me keep the 1/2. Yeah, I think I want to keep the 1/2 for historic reasons, because otherwise it will be perhaps too confusing later on. So that's the Hamiltonian. According to, like, if you look it up, we discussed that this is actually a self-adjoint operator, or if you define it on some nice, let's say, Schwartz functions, then it's essentially self-adjoint and it admits a unique self-adjoint extension. So self-adjoint, or essentially self-adjoint, depends on what domain of definition you choose. And the corresponding Schrödinger equation is minus 1/2 psi double prime plus 1/2 x squared psi is equal to e psi. Again, as before, right? The general story is that for every value of E, this equation has two linearly independent solutions, right? However, we'll now build a very exceptional set of solutions, and it will turn out that for the spectral theory, this will be sufficient. So from this huge set of solutions, we'll choose a very, very small subset. So the people coming from physics, they know what it is. I don't know, people coming from, so who knows what the answer going to be in the audience? Oh, you're not allowed to raise hands, right? Yeah, so, right. Okay, so some people certainly know, some people maybe don't know. Okay, so it starts with the following trick. In fact, first we relate it to a beautiful algebraic problem. So we're going to be solving this equation. Now we forget about the spectral theory, we're solving this equation. So this equation is an equation as usual in functions with continuous second derivative on R. So let me introduce the following notation. A will be 1 over square root of 2 d over dx plus x. So let me denote by A star. At the moment, of course, in the future it will be the adjoint operator, but at the moment we don't care. So I think it will also be one of the exercises to check that actually it is the true adjoint. So let me check whether I got my signs correctly. It is already here clear that naively this is a kind of adjoint. If you don't think about domains of definition, so this is a kind of adjoint because x is self-adjoint, right? And d over dx is anti-self-adjoint because I d over dx is typically self-adjoint, so d over dx is anti-self-adjoint, so when you take adjoint, so you should get a minus sign. So now a small proposition. First of all, the commutator of these two operators is equal to 1, and the operator H is equal to A star A plus 1/2. Now note that I don't, at the moment I'm thinking about those operators defined on something like C2 or maybe C infinity or maybe Schwarz class. So I don't think about the real domain of definition. So I'm thinking of it as a differential equation. So I'm not thinking about it spectrally. So then the proof is more or less obvious. So let me simply write down the composition A star. So what will happen when I compose those two operators? Well, there will be minus 1/2 times the second derivative, right? So there will be plus 1/2 times x squared. And then there will be two mixed terms. So what will be those mixed terms? So this will be 1/2. And here d over dx composed with x minus x composed with d over dx. Right? This is a differential operator acting on some function. So the commutator between d over dx and multiplication by x is equal to 1, right? Because this d over dx may differentiate that x, so there is an extra term equal to 1. Now, if I compute in the opposite direction, a star a, well, the first two terms will not change. But in the second term, these two terms will exchange the signs, because here will be minus d over dx x plus x d over dx. So I don't know, with this yellow chalk, hopefully we'll have enough for today. So this is all equal to plus 1/2, and all this is equal to minus 1/2. Now what? Already the difference between these two expressions is equal to plus 1/2 minus minus 1/2 and is equal to 1, which proves the first equation. And now this, what do we want? We want this, right? This plus 1/2 is equal to the expression for h. Oh, sorry. Is it okay like this? With this implication? It's a bit curly, but... Right, so those two equations. Okay. Now the next theorem tells us the following. So let's introduce the following notation. Psi naught of x is equal to exponential minus x squared over 2 psi n of x is equal to a star to the power n psi naught of x. So then these are solutions of the following eigenvalue equation. Is it what I want to say? Yes. Right? So here is the story. For any E, there are two solutions, right? But now for some very, very specific E's, right? Strangely looking specific E's, positive half integers. I construct very explicit solutions, right? So let me prove it. First of all, let's deal with this guy. And let's note that A, the operator A acting on psi naught of x. So this is what? This is 1 over square root of 2 d over dx plus x acting on exponential minus x squared over 2. Now, I claim that this is equal to 0. Like, is it equal to 0? Yes, it is equal to 0, right? Okay. So this observation implies that when I act by h on psi naught, by the formula that I have over there, it is a star a plus 1/2 acting on psi naught, but a acts by 0 on psi naught. And therefore, this is equal to 1/2 psi naught. Okay. Now, by induction, one can prove the following. So a star to the n is equal to a star to the n a plus a star to the power n minus 1. I actually let you prove it by induction as an exercise, and maybe I just give an indication of a somewhat more elegant algebraic proof. So let me rewrite it in the following way. So I want to compute the commutator of a with a star to the n, right? But now notice that the commutator is a differentiation in our algebra. So what does it mean? This means that it is equal to commutator a star to the power n minus 1 plus a star commutator a star to the power n minus 2 and so on, right? So you take a commutator with each of those terms separately, and the terms which were before it you put on the left, and the terms which were to the right of it you put on the right, right? That's what I'm doing. But now each of those commutators is equal to 1 according to my previous proposition. So all these things, they're equal to 1. So the remaining terms are a star to the power n minus 1. Now how many terms you have? You have exactly the number of terms which is equal to the number of a stars in the formula. So it is equal to n a star to the power n minus 1. Okay. Now I apply h to psi n. So this is equal to a star a plus 1/2 acting on a star to the n psi naught. And well, here I can use the identity that I proved before. So this is equal to a star, and here will be a star to the n a plus n a star to the power n minus 1, right? So that's a transformation of the first term, and then acting on psi naught, plus there will be remaining term 1/2 a star to the n psi naught. Now a kills psi naught, right? So a acting on psi naught is equal to 0. So therefore, the first term is gone. So that's because a psi naught equal to 0. Now I can put all the terms back together again, because I have here a star times a star to the power n minus 1, which is again a star to the power n. So this is actually all proportional to a star to the n acting on psi naught, which means that this is some number n plus 1/2 acting on psi n. So these are the eigenfunctions of my Hamiltonian. Now maybe a small remark. So up to now we were dealing with this thing as a differential equation. A small remark is that in fact psi n of x are of the form hn times psi naught, where these are polynomials of degree precisely equal to n. Why is that? I want to show you, like, one of the exercises for next time will be to actually give some formula for those hns. They're called Hermite polynomials. But why is it true? You see, so this is equal to what? So it will be 1 to the power 2 to the degree n minus 2, right? Now, minus d over dx plus x, and here to the power n, and here exponential minus x squared over 2. Now let me do the following trick. So let me write it as 1 over 2 to the power n over 2. Here I'll write exponential of minus x squared over 2. And now I will write the following. So watch my hands. Is it right? So, you know, I conjugate each of them, right? But that's the same as conjugate the whole thing. And conjugating the whole thing, I compensate here. Right here there was an extra exponential of x squared emerging on the left, I kill it. So this is actually equal to the expression that I had before. All right, now what happens here? I actually can do that conjugation. Minus x squared over 2. And I do that conjugation. What happens when you pull it through, right? So you get an extra one more plus x. And that's it. So this is minus d over dx plus 2x to the power n. So this is a differential operator, but now notice that it basically acts on 1, right? So eventually when d over dx gets here, you should kill it. Now, well, what this expression will be? So this expression will be 2x to the power n plus eventually some lower degree terms, right? Because some of those d over dx's can hit some of those x's. If nothing, no d over dx ever hits an x, you get 2x to the power n, but otherwise you get some other terms. So this is lower degree. So this is a polynomial of degree n, and you even know what the leading term is. Right. So that's the first remark. The second remark is that actually all psi n's are in L2 of R. Well, of course, right, because this exponential, right, it decreases very fast at plus and minus infinity. You add a polynomial growth is really nothing, right? So this, all these things, they're integrable. So actually, we happen to find actual eigenfunctions in the domain of definition, so they are smooth, they are square integrable. So these are just good functions. They're good eigenfunctions of our original Hamiltonian. So eigenfunctions of eigenvalue n plus 1/2. Maybe just a side remark. If this is the case, then it's easy to show by the standard whatever linear algebra arguments that they're L2 orthogonal to each other if n is different from m. So they are eigenfunctions of different eigenvalues, so then they have to be L2 orthogonal. Okay, so now a theorem, and this theorem has a quite beautiful proof. So if you normalize them by their L2 norms, we obtain a Hilbert basis of L2 of R. So maybe just a test question, what could actually go wrong? Right, so they are elements of L2, they are normalized, they are orthogonal to each other. What can be wrong? Why could it be not a Hilbert basis?
Not complete system.
Sure, this would be not a complete system, or possibly, let me start the proof. Let me denote by H tilde. The let me put it in this vague way and then more precise way. So I take a vector subspace of finite linear combinations of psi and tildes, and I take its closure in L2, or, which is the same, I take sums Cn psi n tilde such that the sum of absolute values of squares of coefficients be smaller than infinity. So we have this subspace. And it might happen that this subspace is not equal to the full Hilbert space, right? So the question is whether it is equal or not to H. So let's assume H tilde is a proper subspace of H. So there is something else inside H. So H tilde is closed. So then this would mean that the orthogonal subspace is non-zero. So there are some vectors which are orthogonal to everything. So let's take So let's take a non-vanishing element in this H tilde probe. So now we'll do the following thing. Before proceeding, I will need a small digression. So here is a claim. So the complex exponentials times this function psi naught, exponential minus x squared over 2, are all elements of H tilde. So for all k in R. So why is it true? So I claim that the partial sums for the exponential function, so the partial sums of this form, they converge to ikx minus x squared over 2 in L2 of R. And these guys, right, these are polynomials, and using Hermite polynomials we can obtain all of them. Right? So these things are clearly in H tilde. So since H tilde is closed, if we can prove that, this means that these guys are in H tilde. So why is it true? Why do they converge in L2 of R? So this is because of the following. So let me estimate the norm of the difference, right? We want to know that this guy converges to 0. So why this guy converges to 0? That's because of the following. So this converges to 0 pointwise, right? The exponential series, of course, converges to the value of the exponential everywhere, right? So it converges to 0 for all points x. And this integral is dominated by the following expression. Let me take k to the L factorial, x to the L, and here let's say from 0 to infinity, and this is squared. You see, I kind of replaced all the terms in the tail of the series by their absolute values, and I even added all the terms starting from 0, right? I could only make it bigger. Now, this integral is clearly convergent, right? So this is some kind of exponential function, and exponential minus x squared trumps whatever exponential of a linear function. So this integral is convergent. Now, by the dominated convergence theorem, so these things converge pointwise, and they are all bounded by something which converges. So this means that actually those integrals converge to 0. So dominated convergence implies that the integral converges to 0. So dominated convergence, everybody knows those words. right? Or not? Anyone who does know the words dominated convergence? Good. Okay. So that was the claim. Now, let's finish the proof. So we decided that we have a vector which is orthogonal in L2 to everything. So it means this, right? All those integrals, they vanish. Now let me introduce a new function, v of x, which is u bar of x exponential minus x squared over 2. Note that this function is obviously in L2, because this was in L2, and we multiplied it by something bounded, so it is in L2. But it's also in L1. So this is because this was in L2, and that was in L2, and the product of two elements of L2 is clearly in L1, because it's now integral. Their product is integral because that's simply the Hermitian product. But now, since this guy is in L1, so this expression, I can rewrite it as an integral over r, v of x exponential ikx dx. And all of a sudden, this defines you a Fourier transform of this function v of x. So this is, I think, square root of 2 pi, if I'm not mistaken, times the Fourier transform. And it coincides, since this guy was also an element of L2, it coincides with the L2 Fourier transform. So this is equal to square root of 2 pi f v of k. Now this is equal to 0. But recall that the Fourier transform on L2 is a unitary operator. So the image of v under that unitary operator is equal to 0. But this means that v was equal to 0 to start with, right? But if v was 0 to start with, this means that u was 0 to start with, right? Because like v is 0 almost everywhere, this means that u is 0 almost everywhere. But if it's 0 almost everywhere, this means it's 0 in L2 of R. But then, well, we assumed that it was non-zero to start with, so this is a contradiction in our argument, and this means that this assumption was wrong to start with, and actually h tilde is equal to h. So this is quite an elaborate and elegant argument which tells you that actually, you know, for the spectral theory, like it's strange, right? We just took our chances and we constructed some explicit family of eigenfunctions for some randomly looking eigenvalues, but it turns out that they actually give you a Hilbert basis. But now, since we have a Hilbert basis of eigenfunctions, well, there is nothing else, right? That's the whole spectrum of our operator. There is nothing else. All right, so what will happen next time? We'll continue maybe for 1 hour with examples. And after that, we'll start a really interesting and somewhat complicated story of relation between quantum mechanics and classical mechanics. So we'll do it using differential equations. All right, so that's it for today.